Printed circuit boards are more important than ever before, and creating methods to automate their formation is just as pivotal. However, these methods need some sort of intent understanding due to the huge distribution possibilities of boards. We explore this in this PCB pin fixer within a manipulation setting. So here's a problem in an abstract sense. We have 6 unique pins for this class of PCB board that can be generated in various random distributions due to the random environment generation that I've set. And the issue is that there's 2 pins in the middle, so these 2 pins here, that are causing some problems in these various distributions, and they need to be moved so that the printed circuit board will work. So because of the huge number of possibilities, it's not that we have multiple start states trying to get to a single end state, it's that we have multiple start states getting to very multiple different end states, but they're solving some overall larger goal. So we need to use a method that's able to do intent understanding, and AIRL is this method. AIRL, or Adversarial Inverse Reinforcement Learning, is a continuation of some of the methods that we have seen in class, and it involves utilizing GALE, which is an older method that involves a generative adversarial network, where the generator is an on-policy algorithm like reinforce, called, in my case, PPO, and the discriminator has entropy baked into its objective function to be as random as possible given the expert data and the samples from the generator. And it has new ideas of reward shaping improvement, where instead of a state action reward, uses just a state reward to be more generalized and not memorize the dynamics. So here's the actual system itself, where I hope to employ that. Here's a PCB station, which is just a printed circuit board within Python, where I focus on deep copy for MDPs and embeddings and environment generation, as well as generating expert trajectories via greedy strategies. My ASC is my physics environment that does the inverse kinematics, keyframe interpolation, and converting my logical PCB to a physical object from this to this, and all the things I need to do with it. And finally, my reinforcement learning, where I use OpenAI Baseline's human-compatible AI's imitation library to essentially create parallelizable vectorized environments and my trajectories to train a PPO model that's ready to predict actions. Actions look like this. For me, I use angular actions, but my method is general to any sort of action. Here's the actual architecture and algorithmic run. We create 10,000 unique logical stations, and then we essentially create a model. We test it, and then we run it actually in a physical environment. So here's sort of the random environment generation in action. You can see that it generates different ones. No model is in use here. And here is the actual model in use. You'll see here that it quickly solves it. We found that this does seem to indicate intent learning, because with the right seed, over many, many, many runs, it does have a much less number of moves taken to actually be able to solve the board. There's definitely improvements we can make related to using better models, improving the lower level physics, but with what we've seen, it definitely seems to indicate learning. Thank you guys very much. 6843 was a lot of fun, and I really appreciate you guys listening.